Hi, thanks for joining us. I'm Guilherme Marshall. I'm Director of Automotive Software Partnerships with ARM, and together with my colleague Bernard Rill, who is the segment lead for Zonal controllers, today we'll be talking about this essential component for software-defined vehicles, the zone controller.
If we start from revisiting the vehicle electrical and electronic architecture evolution, in the very recent past, you would see a completely distributed architecture where every single function would actually have a ECU dedicated to delivering that function. This today is leading to massive complexity. A few years back, a mid-size car would already have in excess of 80 different ECUs, and a premium car could have 120, 150 ECUs. That brings a lot of complexity in itself, but also brings on weight and brings on a lot of wiring to connect them one to the other. So for a few years now, the industry has been already deploying a mitigation, which is consolidating some of these ECU functions into domain controllers. This has helped, but not completely solved the problem. And one of the problems here is that each domain controller may have to connect to ECUs that are spread all across the vehicle as well, which means that it saved some ECUs in total, consolidating single functions into a larger and more complex SoC, but it hasn't alleviated the problem with cabling and networking. So in comes the desire to then have a fully virtualized and cross-domain function centralized in the car, a server on wheels, if you will, that will be served by controllers that are located in different zones in the car. These are the zones controllers, and they are no longer dedicated to a single domain or use in the car, but they are mostly focusing in connecting all the ECU sensors and actuators in that region in the vehicle, and bring that onto a central compute element. This is, however, a few years away, and the zone is now accelerating to actually implement a hybrid that maintains the domain controllers and starts to consolidate the periphery closer to sensors and actuators onto the zone controllers that we're talking about today. There is no single definition of zone controllers, however, and even the name is not something that everyone uses. You can find terms like zone, integration, aggregation, concentration. We've seen them all used in a very similar context in the vehicle EE architecture. It's a very diverse range of capabilities as well that each OEM is looking at. There is no set rule book for how to start with the first implementation for a zone controller. So each OEM is looking at the opportunities to consolidate and deploy something that fits better their own existing architecture. But it's not only a variation from OEM to OEM. There is also variation on the zone capabilities required within the very same vehicle. And it is quite likely that we'll see solutions that have a low, medium, high capability of zone controllers distributed within the same vehicle. Apart from these differences, there are some very common traits. And in early stage, in the first implementations of zone controllers, we believe that one of the main purposes will be to serve as a connectivity hub, basically connecting data or consolidating data from the ECUs in a particular region of the car and connecting through a high-speed networking link to either a domain controller or a central compute controller in the center of the vehicle. With that, you'd be simplifying all the cabling that is required to connect the high-speed central compute to the zone. There is also an aspect about power management, which is essentially similar and also involves cabling. But more than that, the leaving local intelligence for power management with the zone controllers means that through the use of smart fuse, for instance, you can have a lot more intelligence in the way you manage power across the vehicle. They can also serve as power conversion hubs, potentially helping to ease a gradual transition into 48-volt architecture. Finally, it will also serve as I/O control. And here is another crucial part of making software-defined vehicles possible, because they will concentrate the low-level functionality and control of the I/Os while leaving the high intelligence, high compute requirements to the central element or the domain controller. So this helps detach even more hardware from software. So all in all, what we believe is that hardware scalability will be essential, from simple implementations that only use microcontrollers to high performance heterogeneous SoC that include real-time processors and application processors in the same system. And the other big aspect is software portability. This will be key for zone controllers to deliver and value and grow over the years as software-defined vehicle architectures get deployed. In this context, zone controllers are a great opportunity for automakers and for suppliers. For automakers, the benefits are fairly clear for most. More than anything, it reduces complexity almost from every factor, every angle you can think of. It promises to reduce dramatically the length of wiring that needs to go around the car. And we can see that just looking at the architecture. There are numbers being put out of about a third of length from a current architecture that would require something like 5 kilometers of wiring altogether. This is not only about having less wires, but it's also about simplifying manufacturing. These cables will be shorter and easier to automate manufacture. And all in all, the reduction in cabling and the reduction in the number of ECUs through consolidation of functions will also benefit departments like procurement and stock management. Obviously, one of the key benefits of this all would be to achieve a lower cost, lower bill of materials, and lower manufacturing costs. And the automation of cabling and fewer number of ECUs will help achieve that promise. With fewer ECUs and less cabling, the whole system will become lighter. And to my surprise, cabling is the third heaviest component in cars today. So the benefits here could be very significant. Finally, this is also about seizing the opportunity to deliver future value and exploring future opportunities for monetization with new functions or further consolidation of functions into the zone controllers as they get more mature over time. For suppliers, what we're seeing is a very fast ramp up of opportunity that can happen starting from 2025. The chart on the right comes from McKinsey and Company, and in our view is even a little bit conservative, as OEMs and tier ones we have been speaking to look to accelerate their programs to zone-oriented architectures. That promise, if you consider that for every car there will be multiple zone controllers, 2, 4, 6, perhaps even more, becomes a good volume opportunity for SoC vendors and for tier ones. And finally, of course, software becomes more and more important, and there is more opportunity for pure software providers to start feeding into zone controllers.
Thanks a lot for this introduction, Jill. As stated, my name is Bernhard Rill, and I'll guide you now towards the zonal controller use case. Within this slide, you'll see a first evolution step. The first integration of zonal controller use cases, since you need to split the wire harness, will most likely focus on body I/O functionality. This functionality includes typical use cases like ambient lighting, some simple sound generation, immobilizer, keyless entry, amongst others. Next, towards the body I/O functionality integration, one clear additional topic which needs to be foreseen within the zone is data compression and encryption. The zone itself will transfer typical automotive buses like CAN, LIN, FlexRay towards Ethernet IP package, so that then this information and those payloads can be forwarded towards the central compute. Classic AUTOSAR integration based on the Flex RTE principle looks alike as outlined in the picture on the right hand side. So you'll have an MCU or heterogeneous SoC design, which includes multiple Cortex-R or M cores. And on top of that, you pin a classic AUTOSAR stack towards this individual core. And on top, there is the RTE, and the RTE includes the logical timing execution, LTE, which then will allow you to synchronize the execution of the individual stacks. Due to that, freedom of interference can be achieved. Moving forward, there will be other types of integration though. As a next step, we think that more configurable options will be used when it comes back towards real-time software stack, mainly classic AUTOSAR integration. So the same functionality as outlined in the slide before, perhaps with a bit of a longer time frame when it comes back towards production, will be integrated as outlined on the picture on the right-hand side. Here you see one updated Cortex-R core from ARM perspective. It's the R52, and one speciality of this core is the exception level 2 separation. So there is a separation kernel which can ensure that normal operating systems which run in exception level 1 can be separated due to this exception level 2 functionality. Due to that, it is as well possible to integrate inherited code or bare metal code. So this was a limitation of the Flex RTE principle. Again, this kind of solution can be used in pure microcontroller designs. Public examples for this one currently which are available are the ST Stellar or the NXP S32S platforms. Or another opportunity for this kind of integration would be the usage in a real-time subsystem of a heterogeneous design. So in case the R52 is being used as a safety island. As a next development step, then the key topic is how much intelligence you can integrate within the zone. So there are now in updated architectures loads of additional sensors which are going to be added. And these sensors produce loads of data. The question is where to process the data, partially, potentially as well. Key sensors, of course, include the well-known camera, radar, LiDAR, or ultrasonic. Once you think that some pre-processing of this sensor data will happen, then you need to add intelligence and compute performance towards the zone. In this context, then the zonal controllers need to include a 64-bit compute component. This could either be a Cortex-A cluster or an upcoming ARMv8R architecture. Well known currently is the CA82. Due to that, you can ensure that real-time software stacks like classic AUTOSAR or even bare metal code can run on the same system on chip next to its adaptive AUTOSAR or even Linux-based operating systems. Due to that, you really can scale up, and with such kind of a design, the goal is, of course, that you have software compatibility, especially on the safety island side with the R52 towards an MCU-based design with the first evolution path of a zonal controller. Next towards sensor processing, there might be other use cases which can be integrated within the zone. As you can see in this slide, there are loads of additional further use cases and complex features which can and could be integrated moving forward in the zone. The opportunities due to that EE architecture involvement are manifold and needs to be defined throughout detailed discussions with the stakeholders, with OEMs and tier ones, what's feasible and doable depending on upcoming EE architectures as stated. So to have a brief insight into what's the use cases that we've as of now heard from the market, a couple of the topics include further display output, for example, within rear seat entertainment. Here then as well, you can have further input sources, display touch input or gesture input. Another big topic, which is ADAS related, is driver and cabin monitoring, including child presence detection. Very much of interest are further AI ML related use cases like predictive maintenance or network traffic and power monitoring. And as a next big application use case, there are all these audio related adaptations which can be partially integrated within the zone. And last but not least, there are these chassis functions, braking, chassis control, perhaps even airbag. All these ones are even ASIL-D applications. So in order to integrate them, the hardware platform and the software development which you'll have within the zone needs to fulfill ASIL-D requirements. How an integration within these functions for the zone will look alike still needs to be defined, and it's highly use case dependent because there are, depending on what application and features you speak about, of course, requirements on latency or real-time responsiveness. One key topic though, which is unique within this kind of evolvement of the zonal controller, is the scalability. So you'll need to scale the zone from a low end towards the high end zone with different operating systems, starting from classic AUTOSAR next towards adaptive AUTOSAR to Linux. And the key goal then has to be, from an application user perspective, to have software compatibility amongst this scalable zonal controller platform.
Now let's look at some of the challenges that all these requirements bring about for zone controllers. If we pick a couple on the hardware and a couple on the software side, we can immediately see that scalability is one of the key issues and challenges for designers when looking at zone controllers that can fit right size compute capabilities at each of the zones of the vehicle and still provide a way for it to grow in the future for more applications and more consolidation. The other thing that we see on the hardware side is a danger of a fragmented way to support device virtualization, which in turn will make freedom for interference slightly difficult to implement with different software stacks having to go in different ways for different SoCs. And I think this brings more cost for the whole industry. On the software side, we're talking about bringing all new capabilities on the hardware, but still some software platforms are slow to adopt some of these capabilities, and therefore making solutions for virtualization and even performance improving capabilities slowly adopted in the industry, and elevating the cost of supporting that with then custom implementations on the side. And finally, obviously, bringing all this functionality onto one SoC is super complex and brings together software from different vendors or from more suppliers, internal, more developers, internal or external, and also a lot more code. This in turn, requires a completely different solution in terms of integration methodology that we see that other industries have already addressed. And the challenge here is to make the automotive industry move towards state-of-the-art software development at scale for it to be able to compete and innovate at a pace that it wants. Also on the software side, we see that tooling is still a little bit immature for large systems that have multiple virtual machines running. And even the fact that platforms are not yet ready for developers, as in hardware platforms, then this makes it difficult to get ahead of the game and start developing and importing functionality. So that can be another challenge.
One of the key topics to enable this integration of these real-time devices is standardization. ARM is actively participating in several industry standardization programs, and within this slide, I'd like to give you a bit of an outlook on these different initiatives. The first one is something which is driven directly within ARM, system ready. Within this project, we define a set of hardware and firmware standards, which, for example, then at the end will ensure that a mainline Linux kernel will boot on the system on chip silicon. And that's very vital when it comes back towards automotive long-term maintenance and security-related bug fixing. So I urge you to check if the hardware platform that you intend to use is really system-ready compliant. The next one is a specification which is currently in the making. It's in the alpha state. It's called the ARM v8R device virtualization specification, and it focuses to ensure that individual virtual machines which running on top of a separation kernel in the ARM v8R architecture can be used in a way that there is freedom of interference when it comes back towards the assignment of individual on-chip modules or devices. In case you like to have an insight into what's that specification at this point in time, feel free to reach out to Jill or myself. And two other initiatives that I like to highlight in this context. One is the Oasis.io standardization work. This is very vital when it comes back towards communication principles in between individual on-chip modules, and it orchestrates as well how a boot process for these kind of modules can look alike. The interesting thing with Oasis is that it's applicable as well for the ARM v8A Cortex-A architecture in this context, so there is a bit of an overlap. And last but not least, I'd like to highlight the ARM participation as a premium vendor in the AUTOSAR community. Classic and adaptive AUTOSAR are a prerequisite within automotive applications, and they're really used widely worldwide. And we, of course, like to reflect the system architectures which are specified within AUTOSAR.
Software enablement is another important area where we invest heavily together with our ecosystem. SOAFEE, or Scalable Open Architecture for the Embedded Edge, is a special interest group that we launched together with industry-leading names in software for automotive. The aim of this group is to provide guidance and evolve open standards that already exist and have been established across other industries for cloud native, and enhance those capabilities to handle real-time and safety requirements as well. The output of this group will be standards and reference open implementation that anyone can benefit from, including zone controller implementations. We also invest on trusted firmware projects. So these are related to secure world implementations, software implementations for anyone to base their implementations on or in fact adopt. We also have strong participation in many open source communities, and to mention a few, I will say Linux and Zephyr as two of relevant community or software projects that touch zone controllers. But also from a tooling perspective, we invest heavily on LVM, the GNU toolchain, and Rust as a new language focused towards safety and security. Finally, to accelerate development ahead of hardware availability, we also invest on ARM virtual targets, architectural models. And these are programmers' view models where developers can start porting and testing their code ahead of silicon availability, or actually use that to scale out testing on a virtual environment like a cloud setting. In fact, for controllers, there is one example available for the ARM V8 R64 architectural model that can be used today. A final piece of the puzzle is specialized compute and development tools. Through our range of Cortex-M, Cortex-R, and Cortex-A processors, we believe that our partners, semiconductor partners, already offer enough choice and scale for zone controllers to be implemented. And our roadmap of safety-ready IP, including not only CPU, but GPUs, ISPs, system IP, NPU, and physical IP, help any partner move along their roadmap and create zone controllers that are even more capable in the future. And finally, ARM Development Studio includes the tools required, including a leading safety qualified C++ compiler toolchain for development of automotive grade software.
So what's next when it comes back towards the zonal controller platform development? The call is get involved. There are multiple things where you can now act upon in order to ensure that this new segment will be really a success story. The first one is collaborate. We need to work together to define common requirements for software abstraction, and how common architectures can look alike as well on the hardware side. This is vital that we ensure that there's no further fragmentation for this new segment. The next one is differentiate. From ARM's perspective, we have loads of individual IP products, including the ones which are outlined below here, which will allow you moving forward to have the best compute for the use cases that you intend to integrate within a zonal controller platform. And last but not least, there will be loads of tools and platforms which can be used to develop such kind of a zonal controller platform. This includes virtual platforms, so simulation environments. You can build upon our functional safety compiler, and you can use Streamline, which is a performance analysis tool from ARM. At the end, from my perspective, there are loads of areas where you can engage. Thus, feel free to reach out to us. Within this slide, you see again our contact details. Feel free to contact Jill or myself, especially when it comes back towards the topic of further discussion how use case integration for a zonal controller platform can look alike and how it can be best mapped towards the upcoming IP which ARM is delivering for this kind of platform development. Thanks for listening towards this presentation. Looking forward in hearing from you.